Hi, I'm Zor. Welcome to Unizor Education. So today we continue talking about Noether Theorem, and the previous lecture was basically a conclusion of purely theoretical and relatively general case of Noether Theorem in extended configuration space. Now, this lecture is about application of the general approach to three different conservation laws: momentum, angular momentum, and energy, which actually are considered as separate cases in some other lectures in this particular course, which basically follow in the menu this one. But I think it's very important to start from something very general and then apply to particular cases. But in any case, in this particular situation, you have basically two different approaches. One is from the general to these three, and then the next lectures will be like a separate proof independent of the general of each of these conservation laws based on Noether Theorem. Okay, now this is part of the course called Physics Plus for All, presented on unizor.com. The website is totally free, and it contains other courses as well. There is no subscription, no advertising, even sign in is optional, so it's all just pure knowledge for your consumption. Now, every lecture has video and textual part, and the textual part is usually, well, at least in the physics part of the course, more, well, precise with more details, because during the lecture, just for saving time, I can skip something. So I do recommend you to basically get acquainted with both the video presentation, whatever I'm doing right now, and the parallel text, which is on the same web page, and you can go into the details. All right, so let me just very briefly remind what was discussed before. So first of all, we did talk about generalized coordinates, which are time and q1, etc., qn. So time is, well, time, and q are space coordinates in this generalized configuration space, which I have actually changed to y0, y1, etc., yn, to have basically unified formula for I with some index, and the index can be from 0 to n. 0 means it's time, and y means the space coordinates. And it does actually make sense, because it makes all the formulas much more readable. Okay, so next was the fact that in the extended configuration space, which contains space coordinates and time as n plus first coordinate, or zeros coordinate, whatever you want to call it. So in this extended configuration space, the motion is represented by a curve, which has basically some beginning and the end. Beginning would be for time 1, which is equal to basically some value, and the ending would be t2, but both t and q and basically y are functions of some parameter, because the curve in whatever the dimensional space can always be represented as parameterized formulas. So every y iota is yi of x, where x is parameter, which is changing from a to b, and in particular y0, which is time at a, would be t1, and y0 of b would be t2. Same thing, every particular coordinate q1, etc., qn from a would signify the space coordinate of the beginning of the motion, and when x is equal to b, so corresponding y of b would be the ending point of motion. And motion is a curve in this n plus 1 dimensional space. Next was a action functional, which basically depends on the whole trajectory. If I'm not using the index, it means basically all indices as a group. So that was basically, on one hand, it's integral from one time to another, and this is Lagrangian of time and all the q's, and its derivative. So that's a regular Lagrangian. So apostrophe means derivative by time, dt. But at the same time, we can do this substitution, since t is a function of x. So I'm substituting the whole integral as integral by x of L of t q prime. These are functions of x, and instead of dt, I will change, since t is a function of x, it would be index in this case by x means the derivative by x times dx, because dt is derivative by x times dx. And then I basically have to replace everything as a function of x, right? Now t is a function of x without a problem, q is a function of x without problem, q prime, which is actually dq by dt, can be converted into dq by dx divided by dt by dx, which is dqx by tx. So if I would change that, my under integral, I will have the function integral from a to b. I put it L, nice, of basically y and yx dx, where y means all the coordinates, which is t and q, as functions of x, and yx is dqx by, not dq, just qx, is qx by q by tx. Okay, derivative by x divided of q divided derivative of t. Now I mean, obviously there are indices, index I, okay, and y0 of x is actually tx. Now with all this, my whole, so this is not a typical Lagrangian, because right now L is equal to L of t q qx divided by tx times tx, this one. So now L is basically function of all y's, and basically y with x index derivative by x, because we now have here from 0 to 1 indices, which means time and space coordinates, and this is also from 0 to 1. Maybe I should really put, instead of this, I will put yi, comma, yix, comma. So the whole group, so we have n plus 1 of these coordinates from time to the last space, and then n plus 1 of the derivative by x. So now it's a function of x, and in this particular terminology we have come up with the Noether theorem, which we have proven in the previous lecture, and I will just put the result here. Okay, the result is, now the action functional should not change with motion, or, which means exactly the same thing, its derivative by x supposed to be equal to 0. What kind of condition we have applied to this functional to be action functional to be invariant? Well, we have to model the concept of motion mathematically. And that we have modeled with transformation of coordinates. So epsilon transformation of coordinates is a mathematical model of motion, basically. So that's how physics is modeled using mathematics. And transformation of coordinates is basically a function. So if my old coordinates were yi, where I is from 0 to n, 0 means time and 1, 2, 3, n means space coordinates, it's actually changed to y epsilon, whatever the epsilon is, some kind of function of epsilon, where epsilon is infinitesimal variable which signifies just an infinitesimal movement. And if my action function, if I will do this, which is basically a speed of change of my function, of my action at epsilon is equal to 0. Now, if this is equal to 0, it means that my functional is invariant, doesn't really change. And that's the main condition from which we have derived in the previous lecture the final result, which looks like this. Something which we call J, which is equal to sum I from 0 to n. This a function which contains Lagrangian times t derivative of t by x, derivative by yx times zeta I equal constant, where zeta I is derivative by epsilon of y, I epsilon. So this is where my yi is converted as a function of epsilon. So this is basically a change in the corresponding coordinate, speed of change of the corresponding coordinates. If y is equal to 0, that's the time. If y is equal from 1 to n, that's the coordinate. And this is the speed of change if we apply this transformation, which means if there is a motion by infinitesimal distance, if you wish, but again, distance in extended coordinates. So if this is the speed of change of the coordinates when the motion starts, then this is supposed to be conserved quantity. And that's basically the end of the theorem, Noether's theorem. Now these things are called generators by each coordinate corresponding. Okay, now what I'm going to do today is apply this to certain conservation laws based on certain very simple motions. So my first motion is, let's just consider that some qk is changing to qk epsilon, which is equal to qk plus epsilon. What does it mean? It means that we are just moving along one particular space coordinate. Time is not changing, and other not equal to k coordinates are not changing. What does it mean? Well, it means that, again, my z is equal to d by dq of yi of epsilon, right? So in this case, the derivative by I is equal to 1. So the zeta k is equal to 1. And all others are not changing, I said, which means there is just, for example, t epsilon is equal to t. So there is no epsilon involved here, since this is a constant. So the constant derivation by epsilon is equal to 0. So one particular zeta is equal to 1, and all others are 0. Okay, so what does it mean for our case? For our case, it means that the j, which is supposed to be the invariant conserved quantity by Noether theorem, will be equal to only for I is equal to k, this thing is 1. For all others is 0. So that probably means this: yk derivative by x. So that's my property, which is conserved. Okay, so now if this is the property which is conserved, well, then what we can do is say that it's okay. Since this property is conserved, let's just consider what this s actually is. It's derivative of L by y, derivative of yk, derivative by yk, and then derivative by x. That's what it actually means. So let's do it this way: derivative by yk of this thing is constant. That's what it means. Sorry, and then derivative by kx, sorry, is constant. Yeah, that's what it means. Okay, and now considering that we know what function L is, let's just see what this thing means. So again, L is equal to, this is Lagrangian. You remember it was t y, and instead of derivative from y by t, we did yx by tx times tx. So this is derivative by x from y, and this is derivative. Well, actually, I can probably have q here, so it will be a little bit less abstract, and q here. Okay. Now we are actually k derivative by yk. Now yk is the same thing as qk, so it's not time, it's a space coordinate. We're talking about only space coordinates right now, so I put it by q. Okay, now we want to differentiate it by qk. All right, if this is the function which is the product of two functions, so my derivative would be derivative by this function times dx plus derivative by this times this. Okay, so let's start with the second one. Derivative by this times this. So that would be just L, right? Because derivative of tx is basically, one second, sorry, no, it's not this. We are differentiating by q, k, x. Okay, so this is I, all the different I, and this is I, and we differentiate by q, k, x, which is here. So only one parameter here. So all other parameters, now usually if you have a function of multiple arguments, it's a partial derivative by first argument, and then from first by whatever we are differentiating. But t is not really dependent on q, k derivative by x. Q is also not dependent on its own. There is only one particular member here. So we have to partial derivative of L by D, let's call it Vk, where Vk is Qkx divided by Tkx. Because this is actually the derivative by time, remember, we just replaced it with this. So partial derivative of this times derivative of this by Qk, which is 1 over Tx. Well, I forgot, but K doesn't have actual index at T. T is without index, only Q has indices. And multiply by Tx. Tx is just a constant this because it doesn't really depend on this. So this is this. Tx, derivative of T by x is cancelling, and now we have dl by dvk. Now this is something familiar. What is this? Derivative of the Lagrangian by speed. Actually, what is Qk x divided by T x? This is, I would say, Q. This is derivative of space coordinate Qk by time. So this is derivative by time, by speed, by Q, okay. Which is what? This is the definition of momentum along the case coordinate. So what we have come up with, that this thing is constant, means this is constant. And this is a momentum. So if my motion is very smooth, yk epsilon is equal to yk plus epsilon, that's what we started from. That means it's the motion which actually is the motion with a constant speed along one particular axis of coordinate. Well, obviously we know that in this particular case momentum is conserved. This is the law of conservation of momentum. What I have just done, I have derived the law of conservation of momentum from the Noether theorem, which we have derived from other properties, from the symmetries of the space transformation. So symmetry of the space transformation in mathematical language looks like this type of transformation of coordinates, and it results in the linear momentum conservation. That's it. That's the first conservation law which I wanted to talk about today. Now, the second conservation law is exactly the same. It's an angular momentum. Now, how do we put into coordinates the motion, the rotation of the solid body? Well, there are two parameters, time and angle of rotation as a function of time, right? There is absolutely no difference between this and this, because we are talking about generalized coordinates. And in generalized coordinates language, in the language of Lagrangian and action functional, there is no difference what kind of coordinates you're using. These are generalized coordinates, not necessarily Euclidean, which basically define the position of the mechanical system. In this case, there are only two coordinates. So n is equal to 1, n plus 1 is equal to 2, so we have two coordinates, time and angle. And the whole thing actually is exactly the same. I'm not changing anything, except I'm calling, instead of q, I'm using the theta angle. Which means that I can put here dl by d theta prime constant which is a definition in the generalized coordinates. This is a definition of angular momentum. So I'm not going to do any kind of a proof. That's the proof basically which I did the first time. Considering the coordinates are generalized, it's exactly applicable to in this case. So that's the angular momentum. And the third one is conservation of energy. This is slightly different, no? Because I mean it's good that I have kind of generalized all coordinates t and q, space and time, as y, but now we are talking about separation of these things. Okay, so what happens with energy? Now, let's say our time is transformed to and all others, I should get my coordinates do not transform. So that makes my generator with an index 0 equal to 1. That's a derivative by epsilon. But epsilon is equal to 1 to 0. And all other generators are 0. Okay, so this is only transformation of time, which means we are experimenting today, and then we are experimenting in exactly the same position, but tomorrow, let's say, not tomorrow, infinitesimal time later, let's put it this way. And again, let's recall our function, the Noether function, that's j, which is equal to sigma from I0 to n. This pseudo coordinates I by x times I is constant, preserved. Now in this case, only 0 is actually equal to 1, and all other indices are 0, which means that j is equal to only the first one, which is L, by y0, which is tx, constant. So derivative of this extended Lagrangian by tx is constant, is conserved. Well, let's now calculate the whole thing, again remembering that CL, let me is equal to L of T Q, and again Qx divided by Tx times Tx. And here I actually mean all indexed values here, group arguments. Okay, so now we have to calculate the derivative by Tx. And again, I will use, instead of this, why is it not running? I will use Vi. Okay? So let's just do the calculation. All right, now in this case we have both components. This is the product. This depends on Tx and this depends on Tx. And we have to differentiate product. So it's this one by derivative of this plus derivative of this by Tx times this one. All right, so it's derivative of, so it's this times derivative of this. So it's L times derivative of this by tx is 1, right? So L is just like a multiplier. Plus derivative of this by tx. Now, the only thing which, well, all these coordinates, Q1, Q2, Q3, etc., they're all divided by the same tx. So that should be sum by I from 1 to n. Derivative of L times by this argument, which is Vi, times derivative of each coordinate, which is derivative by tx, which means this is a multiplier, so it would be qix, and derivative of 1 over tx is minus, so its minus would be here, tx squared, right? Derivative of 1 over tx by tx would be minus 1 over tx squared times this one. So which means this. And, by the way, what is this? Derivative by x of qi divided by derivative of x by tx. Well, derivative by derivative, it's derivative of qi by t, which is velocity. That's what it is. So our formula is this one. This is constant. Okay, fine. So we know this is constant. This is conserved quantity from Noether theorem. My question is, what is this? Well, obviously, in general, you can leave it as this, assuming that Vi is actually Qi prime, which means time derivative. However, in most of the in all cases which we are considering, so all the stationary mechanical systems, conservative mechanical systems, as I have to say, all the mechanical systems, in all these cases, L is equal to T minus U, kinetic energy minus potential energy, right? So, okay. And what is kinetic energy? Kinetic energy in, again, all the conservative systems which we are discussing, it was actually a quadratic formula of the speeds. Like, remember, if you have one particular point mass moving with a speed v, its kinetic energy is mv squared divided by 2, right? So in all systems, when more than one dimension is considered, if you consider this vi times vj, this is I and j from 1 to n. So this is a general homogeneous quadratic form. This is the kinetic energy. The kinetic energy for all these conservative mechanical systems is a homogeneous quadratic form of the velocities, right? Now, if this is true, then what is this particular expression and this particular expression? Well, now we're basically talking about only this. That's important. So it's very easy to prove that this part so again, J is equal to L minus sigma dl times dv height times vi. I will be. So there is a theorem that if L is equal to T minus U and T is sigma Aij Vij, then dl by dvi times vi sigma is equal to 2t. Now this is called Euler's theorem. It's very easy to prove, and the proof is in the notes for this lecture. It's like 3 and 5 lines of code. I just don't want to do it right now. It's very easy to prove, and what's the result of this? The result of this is by the way, u is independent of the velocity, so basically derivative of L is derivative by t. So I can put as well t here. Doesn't really matter. Just put t. By t is this. So what's the result? The result is that J is equal to L minus 2t, which is L is this minus t plus u. Right? T minus 2t is minus t, and minus u is, which is energy with a negative sign. So this is a preserved, conserved quantity. So energy is conserved quantity if we are changing only the time coordinate. From transformation of time, which is symmetrical, which means preserves the action functional, follows the preservation of energy. So the law of conservation of energy depends on certain qualities of our space, which means, well, time space. If you are changing the time in a symmetrical way, so to speak, which means it preserves the action functional, then the law of conservation of energy is a consequence, logical, mathematical consequence of this. Just think about what we have basically demonstrated with these 3 laws, that each law depends on certain symmetry. So my energy is conserved is generator by time is equal to 1 and all the others are 0. My linear momentum is only one particular case generator is equal to 1 and the rest is 0. And angular momentum is also when only 2 coordinates, time and angle, then the corresponding time generator would be 0 and angle generator would be 1. So all these are just different cases of how the transformation actually is done or how the motion is done. So the motion in time, motion in space, if they are symmetrical in a way that they preserve the action functional, from the general Noether's theorem, follows these for particular cases of motion. This is a time motion, I mean change of the time, we are doing the same thing but later, let's say. Or the space, if we are doing the same thing but in a different location. If we are changing time or we are changing the location in a smooth way, in a nice way, so that our symmetry preserved, our action functional preserved, then follow the corresponding conservation laws. Now, There are some other lectures in the same chapter of the course, which is dedicated to Noether Theorem. And these lectures, 3 lectures, are dedicated to these 3 laws: momentum, linear momentum, angular momentum, and energy momentum. But they are actually derived in a kind of from the beginning, without generalizing the Noether Theorem in completely general case, and then going to specific cases. They are just specific cases by themselves, and it's also, certain, it presents certain interesting way of doing this. But I separately defined all these components. I separately proved the preservation of linear momentum, angular momentum, and energy in some way maybe similar form to a generalized, but still some specifics for every particular case. Now, this lecture is about how to use the generalized approach first, and then put into particular cases based on certain values of generators. Okay, that's it. I do suggest you to read the notes for this lecture. These notes are very detailed, and basically all the calculations are correct. That includes, by the way, this, I was mentioning the similar Euler theorem. I proved it in a very, I think, nice way. So I do suggest you to read all these notes. It's very, very important. And obviously, as everything else, the website again is totally free. I recommend you to look all the courses which are there, and there are courses in Math for Teens, Math Plus, Physics for Teens, includes a lot of different components, different chapters. And well, this is already a next chapter of Physics Plus, which is Lagrangian, and then after that I will go to Hamiltonian. All the preparations for something in the future. That's it for today. Thank you very much, and good luck.